Hello. So I've got the pleasure to open ISMIR 2018. I'm Geoffroy Peters with my colleague Slim Essid and Gaël Richard. ISMIR 2018 is a co-organization between Telecom Paris and IRCAM. And I will give you some information about what will happen. So first, let's thank a lot the generous sponsor that we have this year, that you will see all along the conference in the stands, which are in the two corridors. And thanks a lot to our sponsorship share of this year, Blair, for this very nice work. So we're on stage, but actually ISMIR 2018 involved many people, especially our local organizing committee that you will see around with their blue T-shirt, a light blue T-shirt, and of course all the chairs of this year. So we are here at the Cité Internationale Universitaire of Paris, which is a place created after the Second World War to host student meeting. It's a wonderful place full of parks. So there is a park just next there where if it's sunny you can go to take coffee. There is the Parc Montsouris, which is just on the other side of the RER. And please enjoy, if there is sun, to take a walk there to take some breath. So ISMIR 2018 occurs in many places in Paris. So these are the maps that you also find in the website. So we are in the, does that work? Yeah, we are here in the south part of Paris. Maybe some of you went to the DISR headquarters, to the workshop at the CNAM or the workshop at IRCAM. We will also go for the meetup with industry at Station F, and maybe some of you went yesterday to the tutorials. And we will go for a river cruise in this place for the banquet, and yesterday evening you went to the Bastille area. This is another map. For those of you who are not familiar with Paris, the metro map is an exact translation of the map of Paris. So each location in ISMIR 2018 is served by a metro or RER station. So we are here at Cité Internationale Universitaire of Paris in the Adenauer space, which probably you join using this RER. And around this place, we provide on the website a map where you can find some place to have a drink or go for dinner. About the program, as you remark, we provide all day long free coffee, so please go when you start sleeping to have a coffee. It's all day long there will be coffee. Also this year we will provide a lunch every day, including the tutorial. And we will also provide dinner almost every day except this evening. So it will not cost you a lot more than the registration. The program, the program is on the website. Please check very regularly the updates on the website, because the last updates are of course not printed and are on the website, including this welcome reception, not this opening session. So the program is on your badge. Just open it and you will see the program. You have it also in the booklet and it is on the website. So some words about the program. We will start soon the scientific program of ISMIR. We have a 6th session, A, B, C, D, E, F, that will long from today until Wednesday. So Slim Essid, my colleague, will give you more details about the new presentation system of this year. We here in the main hall of the conference, where we will have the oral session. The poster session will be on the corridor and the other corridor. We will have the interactive machine learning for music exhibition right there, and the sponsor all around. Vote for the best oral poster presentation. So this year, actually all papers will be both presented orally and have a poster. So actually, everybody can potentially have the best oral presentation or the best poster. So the system is, you receive with the booklet a form that you should give back to the desk before Thursday morning, and you are able to vote, for example, for this. Oh, this is the paper from the watch or the one from Gabriel, just par hasard. About other part of the program, so we have a keynote today of Patrick Flandrin, who will talk about Fourier, because this year is the 200th anniversary of Joseph Fourier. We will have the ISMIR session preceded by a cocktail during lunch, and we will have Rebecca Fibrink on Wednesday, who will talk about interactive machine learning. Tomorrow morning, actually, we have an extra slot in the program. It will start at 8:30 with a presentation of the 4 installations that you see in this part of the session that followed the call for works using interactive machine learning to create music. New slot, which is not yet in the program, so even Wednesday, you will be able to wake up early if you really like. So at 8:45, we decide to present the award winners of the ISMIR Hack Days that was Friday and Saturday at Deezer headquarters in Paris. So this will be soon on the website. Unconference, the evening we will go for the Unconference. That's also something new this year. We will have a whole evening at Telecom Paris Tech. Maybe some of you already went for the tutorial. This will be in the same location. And we will have a whole conference dedicated to on-the-flight topics. You can already propose your topics in this website. So there was a call on the community mailing list. You can already propose topic of discussion. We will, of course, provide drinks and food. This will be at Telecom Paris Tech. The banquet, yeah, we will have the jam session back to ISMIR. So thanks to Pandora, we will have a jam session. And this will be the first ever jam session on a boat. Also, please participate to the Google Doc for participation. The banquet, you have the map in the booklet. So it will be in Quai de Grenelle. Please follow the instruction in the booklet. We will have a late-breaking demo session on Thursday. So the late-breaking demo session will host 50 posters and 10 Marek submissions. And a new event that we created this year is the Meetup with Industry. We will move to Station F. For a real Meetup with Industry, it's a kind of MIDEM. So we'll have many industry, including probably Apple Europe heads will come to this Meetup with Industry, where as researcher you can meet the industry. We'll have presentation from the industry, also from the European Commission. This will be at Station F. Finally, ISMIR 2018 is a code of conduct that you can find on the website. This is really important because by entering this room, that means that you agree to behave appropriately to the code of conduct of ISMIR 2008. And if ever you have any problem with another person in the conference, please contact one of the board members, one of us, or one of the local committee. Finally, there are many information that goes over the Twitter account, so please register very quickly to the ISMIR 2018 Twitter account. Also post your best picture of ISMIR with the hashtag ISMIR 2018 or on Instagram. Okay.
So we'll have in total 6 sessions with 18 papers per session, following a scheme which is a bit different from the usual one, okay? Each session, actually, will be divided in 2 parts, an oral part and a poster part, so that every paper gets a chance of having an oral presentation and a poster opportunity. Basically, our motivation here is to allow every paper to get the best of the 2 worlds, okay? The exposure that's granted by an oral presentation in a single-track conference like this one, and an opportunity to conduct in-depth discussions about your work, which can only happen during poster sessions, right? So, as a consequence, to have all talks fit in, the presentations will be shorter than usual. We'll have 4-minute presentations, okay? Questions will be left for the poster session. We will have no time for questions during the oral session. This will happen later. And this means we're expecting all our speakers to finish their presentation on time. That's very important. We actually are going to help you keep track of time by showing you, speakers, on this screen here, a countdown. Our session chair will be controlling that countdown through our timekeeper, okay? 30 seconds before the end of your talk, you'll get a first notification, okay? And by the end of the presentation, another one. And if it's still not clear that you're out of time, and hopefully, then real applause from the audience, okay? So, has to be clear, no time for delays. A reminder also for speakers, you have received instructions, and this is also on the website. Please send us your slides in advance so we can have them ready for you to be displayed using one of the conference computers. Everything, the setup is good, it's been thoroughly tested. Everything should run smoothly. We have a Mac and a PC, okay? If you haven't received these instructions, get in touch with us. Something went wrong, shouldn't happen. Some new actually initiative for the first time in the history of ISMIR. These sessions are being streamed live on ISMIR 2018's YouTube channel. Please help us spread the word. And of course, we will only be able to film those speakers who will have given us prior written consent. This is happening before the sessions. Don't worry, if you don't want to be filmed, just check the right box on that form that will be handed to you before the session, okay? Right after the oral session, we have a coffee break, and we go to the poster session where the same speakers that will have presented during the oral session are there to answer all the questions you might have about their work. And this is, again, a good place for in-depth discussion, okay? Another small reminder for speakers, please take the time to install your posters before the oral sessions, ideally, or during the coffee break. This morning, everything is running smoothly. All posters are already there. And of course, please be there for the audience, for the participants to ask you questions about your work. I'm now going to leave the floor to Gaël, who's going to give you some statistics.
Okay, thank you, Slim and Geoffroy. As you can see, there is not only authors who want all to present orally, the chairs also want to present orally all, so that's why we all present in a row. So I'm going to give a few statistics of the conference. I think it's always interesting. So we had 235 valid submissions. So, I mean, as you know, ISMIR is following a double-blind review system, a two-tier review model. And we had 269 reviewers, 60 members of the committee, and each paper was assigned to one PC member and 3 reviewers. So this is a total of 940 reviews and meta-reviews. And finally, we obtained 104 papers with an acceptance rate of 44%, which is about equivalent to the previous years. Maybe it's slightly lower acceptance rate, but it's really slightly. But of course, the difference is that our paper will be oral and posters. So if we look at the accepted papers along the years, you can see that we are more or less in line with the previous years. In fact, at least from 2012. If we look at the number of unique authors, again, it's the same. We are about in line with previous years. There is no much more difference. If we look at the accepted papers per country, these statistics only include the institution of the first author. You can see that we have quite few papers from the States, France, Germany, Austria, United Kingdom, Taiwan, and gradually less and less amongst countries. But I can mention that we have papers from Uruguay, we have paper from Brazil, so we can really see that it's a world issue. If we look at the entities, it's about the same distribution, or more or less, but we have more countries represented. So from India, from what country I have not been before, Israel, and so on. So we have much more countries represented in terms of institutions. If we look in terms of attendees and number of people attending the conference, you can see that the number are fairly high, and we will see compared to the previous years. So 442 for the main conference, 470 for the meetup with industry, because it was possible to register only for the meetup with industry, and 275 for tutorials, which is quite high also. And you have noticed that this year we had 2 tutorials. I mean, if you chose to be in the tutorial, you had 2 tutorials for the same price. I mean, for the same ticket. So. If you look at the attendees over the years, and as also that you have been informed, that we are many more attendees than previous years, and this is also why it explains that we had to declare the conference sold out for the main conference, but especially for the social events, but also for the main conference. So we have over 400 people, and you can see that if the green and red bars are about the same, the blue line, which is the attendance, is much higher. Okay, so some other facts. So the gender issues at ISMIR. So we have about 1/5, which is women. Of course, that it's not very easy to make this kind of statistics. So to make the statistics, I had to look at all the first name to see if it's a female name or main names. And no, of course, I found another trick to do that. And other gender facts, still linked to men and women. So in terms of first author, it's about the same as the audience, but if you look all authors, the distribution is more unequal. But in terms of chair and in terms of local committee, the distribution is quite good. And in terms of attendees, it's the same number that I've just showed. So that's it that I wanted to present. So welcome to Paris, welcome to ISMIR, and we hope that you will have a wonderful conference. And so now the only thing I have to say, let's start it. Thank you very much. So I have just a final word. We have a cloak room, so don't hesitate to use it if you don't want to carry your bag around. So it's open all day, and it's secure because there is a person in front of it all the time.
Okay, so welcome to this morning session, the first oral session of ISMIR. It's entitled Musical Objects, as very broadly titled. So the first speaker is going to be Roman Gerhardt, talking about a confidence measure for key labeling. Just some practicalities. We have, as Slim mentioned before, 18 4-minute presentations. This is going to be a bit of a challenge. Hopefully we get through with this, and with a target time to finish at about 20 to 11. Over to you, Roman.
Yeah, so good morning. My name is Roman Gebhardt, and I'm going to give you some information about our paper, a confidence measure for key labeling. So we establish a measure for the likelihood of a key classification to be correct. For that, we developed 2 features which independently both contribute to a global confidence score. One of these is keyness, which expresses the amount of tonal content held by the audio, and the second, stability, is derived from the steadiness of key classifications throughout the whole track. So on the first feature, this is derived from a chromogram representation, which is reduced to tonal content. With it, we assume the necessity of sufficient tonal information held by the audio. Our main focus is in electronic dance music, where this is often not the case because it is often purely percussion-based. We can have a listen to that. So in this first part, just percussion, and in the middle part here, we have sufficient tonal information for a key detection, and this is also where there is a high value of keyness. Okay, we'll go on with stability feature, which is derived from the distribution of local key classifications throughout the whole track. We measure the circular variance of this key path. In this example, we have a very stable key path, which makes a correct key classification likely, which is not the case in the following example, where we have a very flat distribution because the key classification spread wide over the circular fifths. This track, we can also have a listen here. Does not follow a classic Western key structure, which is also which makes a global key label obsolete. So finally, on our results, in a listening experience, we could show high correspondence of listeners' ratings with our developed features. Tracks with correct key classifications score significantly higher in confidence than those with mistaken key labels when we applied a state-of-the-art key detection algorithm. And finally, we could clearly improve key detection results by special treatment of tracks with low confidence score. I don't have enough time to show you that now, but we can talk about that in the poster session. Thank you very much.
Thank you, Roman. So the next speaker is Filip Korzeniowski from Johannes Kepler University, talking about improved chord recognition by combining duration and harmonic language models.
Okay, hi everyone, I'm Philip, and today I'm going to talk to you about my recent work on key recognition. Just to give you an overview, the overall structure of a key recognition algorithm is like, why does it go on automatically? That's weird, okay. It's like that, so we have like the audio signal at the bottom, and we have an acoustic model that goes over this audio signal and predicts a chord for each snippet of the audio. And then we have a temporal model that kind of aggregates these predictions of the acoustic model over time and outputs coherent segments of chords. And the acoustic model is usually like it used to be Gaussian mixture models. Nowadays, almost everybody uses deep learning for obvious reasons. But there was little work on temporal models. And the reason is because they it was shown that they don't model the musical relationships of chords very much. And what we showed in our previous studies is that it's because they are actually operating on the lower level, so basically operating on the same sample base level as the acoustic model, meaning that all they see is just like they tend to predict the same chords over and over again because that's what they see during training time. What we're trying to do is to split this temporal model up into two models such that we have a language model, a harmonic language model that actually only sees the chord changes such that it can easier learn to understand what's the relationship of, for example, C major to G major. And a second model called the duration model that actually models how long these chords are usually being played. And this work basically presents a probabilistic way to combine these two models with the acoustic model and shows different ways to model the language, the harmonic language, and the duration. Yeah, so for the language model, we tried different possibilities, like very simple finite context n-gram models with like history of length 1 or more, and recurrent neural networks. And what you see is that, of course, recurrent neural networks work much better. The yellow line would be the baseline. So we can improve like the prediction of the next chord by a large margin. And the interesting thing is that actually, if you look at what the RNN learns, like the input embedding it learns for the chords, we see that they are like clustered in a way that has some correspondence to how they are positioned in the tone nets. And I would be very happy that some musicologist comes over to my poster and explains why this is happening, because I have no idea. The second thing is that we did the same thing for duration models. We tried some simple statistical-based models that just take into consideration the overall distribution of chord lengths in the data set. That's like the first two, and they don't work very well. But again, if you use recurrent neural networks, life is much better. And the reason is that they basically can adapt the harmonic rhythm of a song, so they understand, they adapt to the song how quickly the chord changes, and thus can model the probability of a chord change much better. And if you combine those, we actually see an improvement. So this is like results for a neural network acoustic model. The better the log probability of the language model, the better the result. And the same is true for the duration model. So the lines are duration models that get better and better. And if you want to discuss these results in more detail, come to my poster. Thanks.
Thank you, Philip. The next talk is by Tristan Garceau. He's going to talk about using musical relationships between chord labels in automatic chord extraction tasks.
Hello, everyone. So I'm Tristan Garceau, PhD student at IRCAM, and I will present our paper that deals with the use of musical relationships between chord labels in automatic chord extraction, written with Jérôme Nica and Philippe Essling. So the starting point of our study is that many works on chord extraction generally focus on the models and not on the chord representation. And part of the community points out the need to rethink the whole paradigm of chord extraction because we observe a decrease of the improvement rate of the classification score. This is why we decided to study the impact of using the musical prior knowledge underlying the data annotation, which is chord labels. Then our proposal is to introduce chord distances that take into account the harmonic content of chords. Also to reduce the chord label before the training with alphabets of different sizes. And also we introduce new kind of analysis. Our results show that we obtain best classification score with musical distances, and also that we obtain what we call weaker error. To perform our analysis, we rely on a probabilistic model, which is a convolutional neural network, which is one of the most performant models in chord extraction. And we trained our models on isophonics dataset, where each audio frame comes with a chord label. We then choose 3 different alphabets and 3 different distances for the three alphabets, the first one is a major minor, and then two others that are more and more precise. And for the distances, we use the classical binary categorical classification distance, and also two other that embed musical information. We then do a combination of these three alphabets and these three distances in order to train 9 different models. And with this model, we evaluate them with a quantitative analysis, which means with a classification score, and also in a qualitative way by observing the musical relationships between target codes and predicted codes. For the quantitative analysis, we use the MIR-eval library, and we observe that we obtain better classification score by using our distances on the major minor alphabets. And we see also that we have no major improvement for the classification score on the other alphabets. And for the qualitative analysis, we developed a specific analyzer. And we observe that in general, numerous classification error nevertheless give correct harmonic indication. And also by using the chosen musical distances, it better preserves the harmonic functions. So our conclusion is that automatic code extraction could benefit from the use of musical distances. And also, if the goal of code extraction is to extract and formalize the underlying harmony, we could introduce the notion of equivalence classes in terms of harmonic functions instead of considering exhaustive chord qualities. So, thank you. See me at the poster.
Thank you, Tristan. The next talk is going to be by Stefan Lattner, who's now at Sony, and he's going to talk about a predictive model for music based on learned interval representations.
Hi, I'm Stefan Lattner from Sony CSL Paris, and most of this work has been done at the JKU in Linz. I'm starting with an example. This is a highly structured sequence, and it actually just consists of a short musical fragment which is copied and shifted over and over again to form this sequence. And we probably all agree that it is a very important property in music to have such structures and to have repetition and self-similarity and transposed repetition and so on. And it is crucial to understand that actually RNN or a convolutional neural network, as we use it now, they cannot learn repetitions, they cannot learn transformations like this. And that's why I propose this model. It's a recurrent gated autoencoder, and it's basically an RNN with relative pitch perception. So it consists of a gated autoencoder and an RNN on top. And the gated autoencoder is capable of turning absolute pitch input into relative pitch representations, like interval representations. And these are represented in this latent space, MT plus 1, and fed forward to the RNN, which learns to predict intervals given intervals. And this is really nice that we can now learn actually such copy and shift operations of musical sequences, like in these very simple examples, but still. I trained an RNN with GRUs and a recurrent gated autoencoder on lots of different transposition and structure schemes, like different transposition distances and different fragment lengths. And if I input the beginning of such a scheme with a fragment the models have never seen before, the recurrent gated autoencoder can just go on and continue this sequence. And the RNN has a hard time doing so. It should actually generate this green sequence, but it generated the red sequence. And we see the hidden unit activations of the recurrent neural networks below these sequences, and we see that the recurrent gated autoencoder has a very repetitive hidden unit activation over time, because it just applies over and over again the same transformation to the fragment, and it doesn't care about the fragment, it just cares about how to copy it. And we can also use this model. This is just a graph to see, okay, the recurrent gated autoencoder really has a precision of more than 99% on this dataset, and a few outliers, basically. So we can also use this model for music prediction, the well-known Essen Folksong collection, and our model is here the yellow one, and the best performing model so far was the green one. And And it's also nice to see that we can combine the recurrent gated autoencoder with an absolute pitch model. With the best performing model is the red arrow. It improves the results substantially. And consider that here we only need 16 hidden units in the recurrent neural network and outperform the best performing model so far because we operate on intervals, basically, learned from absolute pitch input. So if you're interested in this, just visit me at my paper, and I'm happy to tell you more about it. Thank you.
Thank you, Stefan. The next talk is by Miguel Roman from the University of Alicante. He's going to talk about an end-to-end framework for audio to score music transcription on monophonic excerpts.
Good morning. The goal of this work is to perform audio to score music transcription in an end-to-end fashion and using deep neural networks. We know that this task is very challenging, so this paper we are focusing on validating the approach on monophonic excerpts. Given this audio that is playing, we know that it's very easy to get the notes and the durations of the rest as well, but a more interesting output for a musician would be the full score, which contains more information, such as the clef, the time and key signatures, and bar lines and rests, durations. So we aim to try to discover whether it's possible to do this audio to score with these simple excerpts. Many works address this audio transcription, but few of them do it in an end-to-end fashion. Do it with the full score. So what we are trying to do is doing this audio to score with the advantage that there is no need to align between the inputs and the outputs because we are doing it in an end-to-end fashion without requiring several stages. So in fact, we're using a database of plain and easy encoded symbols to get both the inputs and the outputs that will be trained to our model. Of course, we're using random tempos in the audio synthesis to ensure the variability of note durations. The audio to score task can be formulated in a similar way to the speech recognition task because the inputs and the outputs are of the same type. So we decided to use a convolutional recurrent neural network, and as it has been proven to be the state of the art of speech recognition. Here it's important to note that we're using the CTC loss, the connectedness temporal classification, that does the trick of allowing us to avoid the need of alignment between the inputs and the outputs. And following the analogy with speech recognition, we are using the same metrics like word error rate and character error rate, and we're also adding some metrics from Nakamura et al. For multi-pitch estimation, but we are adding note durations and as well as we're measuring everything with rests. As you can see, the model can make good predictions of most of the symbols, but it struggles with symbols of ambiguous nature, such as clef and time signatures, and also some ambiguities with ties, as you can see in the picture below. So we believe that we are opening up a new avenue of audio to score music transcription with some advantages over existing methods. So the first one is that there's no requirement of alignment between the inputs and outputs, as we have mentioned, and this avoids the ambiguities, although we have other ambiguities in the musical notation. Outputs are musically meaningful, meaning that they can be directly performed. Also, this is an end-to-end approach, avoiding cascading of errors of several stages, and we can learn musical models in the same way that speech recognition learns language models. We are aware this is a simple, of the nature of these experiments are very simple, so the next steps, but these are the basis of our future work. So the next steps is polyphony, obviously, but we are also exploring different alternatives in the inputs and outputs and training with different time bursts and real audio datasets. Thank you very much if you're more interested.
Thank you, Miguel. The next talk, paper A6, will be delivered by Andrew MacLeod from the University of Edinburgh, and he's going to talk about evaluating automatic polyphonic music transcription.
Okay, thank you. So sort of a related topic, I'm going to be talking about evaluating automatic music transcription and specifically polyphonic music. And again, sort of an overview of the task. So what we do is you start out on the left in automatic music transcription, you start out with sort of a waveform, and what a lot of systems do is they just perform multi-pitch detection. So they just output this format in the middle, which looks like MIDI or a piano roll. But what we're interested in, what we really want models to do, is to go all the way to a musical score. And again, that requires a lot more information. That requires key information, note values. It requires voicing information sometimes, metrical information. And the question is, how do you evaluate that in a musically important way? So we are proposing a new metric, which is, number one, it's automatic, quantitative, and it's joint. So it outputs a single number given a transcription. But another property, it's also modularized, and that's for two reasons. One, for wider application, so you have a lot of models that maybe only perform a subset of the full, complete transcription process. So we want to be able to use our metric for those models as well. And also for useful feedback. So this metric will be able to tell you, okay, maybe your model is doing very good at this aspect of the transcription, but you need to work on this aspect of it. And one important property that we have is that of disjoint penalties. So what that means is mistakes are only penalized once. And so this is a problem in transcription. You can often, if you miss a note, if you put a note in the wrong spot, that can have cascading errors. Maybe then you don't want to also penalize that model for missing something in voice separation where the error is just due to that multi-pitch error. And this is a novel property of our new metric. So a quick example here. Let's say you have, so at the top, this is a minuet in G that you guys may all recognize, and then we have two example transcriptions of it. And what you can see is neither one is perfect. They both make mistakes. They make different mistakes. Some of them are better at multi-pitch detection. One of them makes an error in the meter. There are some harmonic errors. You have note value errors, voice separation errors. There's all sorts of errors. But the question is, how do we tell which of these transcriptions actually is doing a better job and in what ways it's doing a better job? So we identify all these different errors, but it's getting that final number that's very important, and that's what our metric allows you to be able to do. So in conclusion, I think this metric, it's a good start to the discussion. I mean, I'm not saying that this has to be the metric that everybody uses, but it's an important topic, and I think it's a good discussion to have. And in particular, the property we have of disjoint penalties, I think is a very important one, and we took a lot of care to make sure that the metric does handle that. Future work is going to align the scores that our metric gives out with human judgments of transcription, which is a slightly different problem, you might say, but it's something that we want to work on. And the code, the metric is implemented in Python. It's available online. Feel free to check it out, and please come talk to me at my poster. Thank you.
Thank you, Michael. Continuing on transcription, the next paper, A7, is going to be presented by Curtis Hawthorne from Google and is entitled On Sense and Frames, Dual Objective Piano Transcription.
Hi, my name is Curtis Hawthorne. I also go by Fjord, and I want to tell you about Onsets and Frames, our automatic piano music transcription system. So first, a big thanks to all of my co-authors, in particular my co-first authors, Eric Elson and Jarlin Song. All right, so Onsets and Frames is our system for going from piano audio to MIDI, and we do this with a deep convolutional and recurrent neural network. For training and evaluation, we use the MAPS dataset. For training, we train on the synthesizer recordings, and for testing, we use the pieces that were played on a physical Yamaha Disclavier, because we believe that best represents transcription tasks in the wild. We call it onsets and frames because we have two subnetworks, one that's trained for predicting onsets, just the first few frames of a note, and the other that's for predicting frame by frame which pitches are active. There's also another subnetwork not pictured here for doing velocity estimation. It looks just like the onset network. So here are our results. So definitely want to give a big shout out to Sigja and Kels for the great work they did in 2016. Our work builds directly on their ideas. So we're very happy with our results, especially the over 100% relative improvement on the note with offset F1 score, which we believe is a key metric that most represents human perception of transcription, especially when you include velocity. So let's watch a demo. All right, and we've continued to improve the model since those results. We'll be announcing a model with improved results soon, but I wanted to give you a preview of that and how well that model performs in even an imperfect recording environment. And big thanks to Eric for doing the piano on that. So as the end of the video implied, you can try this out yourself with our new Piano Scribe app, thanks to some awesome work by my colleagues Adam Roberts and Monica Dinculescu. They've actually ported it to JavaScript so you can do transcription in the browser. And if you stop by the poster session, I'll have a laptop and you can try out a live demo. Thanks so much.
Thank you, Curtis. The next talk will be given by Carl Southwell from Birmingham City University. It's entitled Player versus Transcriber, a game approach to data manipulation for automatic drum transcription.
Hi, thank you. I'm Carl Southwell, and today I'm presenting Player versus Transcriber, a game approach to data manipulation for automatic drum transcription, which is work I did with Ryan Stables and Jason Hockman at Birmingham City University in the UK. So, as in many fields, one of the major challenges in automatic drum transcription is the lack of training data. So one approach to overcome this is to create new data from existing data using data augmentation. So for example, for images, you might increase the brightness or rotate the image. Data augmentation techniques also exist for audio, for example, the Mudder library, which allows you to pitch shift, time stretch, add noise, and compress. And these have been utilized in recent automatic drum transcription systems and have demonstrated slight performance improvement. However, they contain a couple of disadvantages. First of all, they require a lengthy parameter tuning process, And second of all, they usually depend on a single set of global parameters, so they are not adaptable to different contexts. To overcome these limitations, we propose the player-first transcriber model, which takes influence from generative adversarial networks and incorporates data augmentation in the model itself. So all stages apart from the player model are the same as existing automatic drum transcription systems, and the player and transcriber model are trained in a two-stage iterative process where the player model aims to manipulate data to decrease the transcription accuracy, and the transcriber is trained to increase transcription accuracy. So the player model performs data manipulation in two ways. First, data augmentation, where it alters each amplitude value of each time step and frequency bin of the existing data. This is also done to isolated samples, which are used in the second stage, which is sample addition, where new drum hits are added to the existing data using generated locations. So this whole process is done using generated variables from convolutional neural network, and the whole process is differentiable, so it can be trained using backpropagation. So we implemented three variations of the player-versus transcriber model. First, org-exist, where it utilizes existing training data and the data augmentation stage. Then org-exist, which uses the full player model. And finally, generate, which doesn't use any existing training data. We also experimented with two sample libraries. So first, where the samples were extracted just from the training data, and secondly, where the samples were extracted from online resources. And we evaluated the systems in two training strategies, which are from the automatic drum transcription overview article from earlier this year. First, random, where the training and test data is similar, and second, subset, where the training and test data is less similar, and this aims to measure generalizability, and we used these 4 datasets in both cases. So we compared the systems against two baselines. First, a model without the player model, and secondly, one where the player model is randomly set. And we found that in both training strategy cases, org-exist and org-exist achieved higher results than both baselines, with high results being achieved in the subset case, which suggests it improves generalizability. Also, we found that using samples from training data is more better than using samples from online resources. And although the generate model does not achieve comparable results, it does allow good results relative to it doesn't require any human annotation. So example code is available on my GitHub, and also this will soon be incorporated into my open source automatic drum transcription libraries. Thanks for watching, and come to the poster if you'd like more information.
Thank you, Carl. The next talk will be delivered by Nat Condit-Schultz from McGill University, entitled A Flexible Approach to Automated Harmonic Analysis, Multiple Annotations of Chorales by Bach and Praetorius.
All right, so I'll be talking today about annotating symbolic music corpora with chord transcription, so a little change of pace. So we're working on a flexible approach to automated harmonic analysis, looking at chorales by Bach and Praetorius. Now, harmony is a central feature of Western music, and obviously, as we've even seen today, identifying harmonies in music is of central interest to music theorists, to musicians, and to music information retrieval researchers. However, as much as we like to think that harmony is this objective, well-understood feature that we can just identify at any point in music, every point in music has some chord that's the correct answer, harmonic theory is still actually quite vague and complicated, and there's a lot of details that you get disagreement between different theorists. So some of these things include things like what types of harmonies are actually syntactically legal. So what set of chords do we allow? Are there 7th chords, 9th chords, add 6 chords, sus chords, etc.? A very tricky one is how do you distinguish chords that are very similar to each other, that share notes or that are subsets or supersets of each other? And then when you're getting into the nitty-gritty details of harmonic analysis, how do you interpret melodic decorations that are, when they're consonant? If they're dissonant, we know that we have to explain them in some way, but if they're actually potentially consonant, how do we decide what to do? So if you give two different music theorists the same piece to analyze, you'll often get two slightly different analyses. And this is obviously a problem if you're going to generate annotated data to use as ground truth data, or just if you, for whatever purpose, this inconsistency and this ambiguity is a detriment to our ability to train or to learn about harmonic theory. So our approach is to develop a new type of rule-based generated harmonic annotation data from the symbolic music, but not to create one specific analysis of any piece of music, but to try to identify all the different ways you could possibly analyze that music given the basic constraints that everyone agrees upon. So once we've generated all these possible analyses, we can compare them, or we can filter out specific analyses based on whatever criteria we might be interested in, like prefer analyses with the fewest chords or the most chords, or forbid escape tones, or what have you. So we're working with chorale music right now. It's the sort of simplest music which is widely used in harmonic theory pedagogy and in harmonic theory research because it sort of lends itself to this stuff. Specifically, the 371 chorales by Bach, which have been studied a lot. We also have a new data set of 200 chorales by Michael Pretorius, which is about 100 years older music. And we've created this data set from scratch and are now going to be sharing it with the community. So in short, the way our analysis work, and I'll be able to go over this in detail at the poster, is, like I said, we define a precise set of rules that are general about what the minimum constraints on harmonic analysis, tailored specifically for chorale music. We then identify windows in the music based on a simple heuristic. And then for each window, we identify every possible way you can divide that window rhythmically that's legal, and then every possible combination of treating notes as being passing tones or neighbor tones or whatever. And you can come up with, in this case, there's 4 different analyses of this window that you can come with just triads. If you allow 7th chord, there's actually more possibilities. All right, so we're sharing this data at a GitHub repo. Obviously, you can't share this data in quite the same way that most annotation data is stored because you can't just align it all with music. So I actually have created an R package which has an API to allow you to filter out as many different types of analyses as you like very quickly. And there's actually a GUI I've set up that you can get to through the GitHub page. So I'm going to thank my sponsors, and I'll be happy to tell people more about it at the poster session. Thanks.
Thank you, Nat. The next talk will be given by Tejaswini Kelkar from the University of Oslo, entitled Evaluating a Collection of Sound Tracing Data of Melodic Phrases.
Good morning. The title of my talk is Evaluating a Collection of Sound Tracing Data of Melodic Phrases. The main motivation for doing this this is not a classic ISMIR problem, but the main motivation comes from our concept about embodied cognition, which is that perception of music is, music learning is a physical activity, and sound and action are perceived as a whole unit. And that we perceive music as an embodied phenomenon. I am mainly interested in melodic contour. There have been alternative approaches to ISMIR suggested in several papers by Kaneshiro, Liam, and several other authors, that we can use different types of data for a ISMIR-like approach. So that's where this research comes from, and is motivated by, I'm mainly interested in modeling contour and contour perception, and there have been lots of symbolic and signal-based methods to deal with contour perception, but a lot of them have the embedded notion of pitch verticality, and to ask people to draw out what melodies might seem like to them seems like a trivial problem, but it isn't, because complexity starts to appear because of our humanness. We tend to amplify smaller changes and tend to not think about larger changes as being large enough if they occur as a pattern. So this is the type of experimental data that we deal with in the lab, and this is a typical example of a sound tracing experiment. This is somebody drawing out a melody. And so this is the data that I have. We evaluated this data with 16 melodies and got people to get into the lab and trace out these melodies as they were hearing them. And then we do a multiple extraction of, so we don't know what we're looking for. We're looking for correlations between these two types of data. And we know that there's some similarity from just inspection. We can gauge that people are performing the task correctly, but how to evaluate this using measures. So we extract multiple features and create label sets, which allow us to capture the different ways in which correlations might be occurring, and also come up with a longest run length measure, which I can explain in detail in the poster, but that creates a significant improvement over what we achieve through canonical cross-correlation analysis, which is a typical way of approaching multimodal paired data sets, such as the one that we have. So this is our evaluation system. We improve it using both handcrafted features like longest run lengths, but also using a deep approximation of CCA. And briefly, the takeaways are that longest run lengths seem to be a feature that improves correlation, suggesting that the salient most slope of a melodic phrase seems to be correlating somewhere with body motion, and hopefully this can be used in improving both data sets as well as methods for retrieval. For this, the data by itself is nonlinear, so a deep approximation performs better, but it could still be improved, and the finer numbers are on the poster and in the papers, and we can discuss this more then. Thank you for your attention.
Thank you, Tejaswini. The next talk will be given by Dogach Basaran from Telecom Paritech. It's going to be about main melody estimation with source filter NMF and CRNN.
Hello, everyone. I'm Doğaç Başaran. I'm a postdoctoral researcher from IRCAM. And today, the subject of our paper is about main melody extraction, which is basically estimating the fundamental frequency of a dominant melody. So what we propose here is a convolutional recurrent neural network whose pre-training is based on a source filter NMF model. So what we propose is not an end-to-end system, but we first train a semi-supervised model to obtain an initial salience representation, which we call the pre-training stage. So then we feed these initial salience representations into a deep convolutive network, then into an RNN stage, where we do the temporal tracking, and in the final classification layer, we have one class for non-melody, and the rest of the classes represent the target F0s, so that the system is able to automatically identify if there is melody or not, and if there is melody, it estimates the pitch. So the main bottleneck shared among all melody estimation methods is finding a good salience representation. Our solution for that problem is that we first start with a good enough salience representation, then we apply a deep convolutive network to enhance it to obtain an even more discriminative salience. So this is where we use the source filter NMF model to obtain a good enough initial salience representation. Here you see the equation, the definition of the source filter model. Roughly going through it, the first part represents the source and the filter part, which describes the dominant melody. Then it is instantaneously mixed with the background, and each of these elements are modeled with an NMF, standard NMF, where there is a dictionary W and an activation H. Here the main trick is you design WF0 in advance such that each of the columns represent a target F0 spectrum, so that the activation of that basis will give you when in time that F0 is activated. So it is inherently a saliency representation. So when you compare HF0 to a simple time frequency representation such as CQT, you see that HF0 is a much salient representation which is more sparse and enhances some of the frequencies much better. I will skip that. So in the experiments, we trained different network variants with HF0 input and CQT input, and we interestingly discovered that when we train an HF0-based system, 40% of the training data is sufficient to obtain an overall accuracy performance of a CQT-based system which is trained on the full training data. And we tested our system on several aspects, and I'll be happy to give you the details in the presentation. But the bottom line is that the proposed system achieves, even improves upon the state of the art with low complexity network models and rather small amount of training data. And we observed that with better initial saliency representations, you can actually get better results. So actually, if you're able to improve the initial saliency, for example, by some modifications on the source filter model, then you can achieve even better results. So a clear future direction will be joint training of source filter NMF with a network, which is not an easy task. So thank you very much for your attention, and I wish you a very good conference.
Thank you, Dagach. The next talk will be given by Li Su from Academia Sinica in Taiwan, entitled Functional Harmony Recognition of Symbolic Music Data with Multitask Recurrent Neural Networks.
Okay, so good morning, ladies and gentlemen. So I'm going to present the paper titled Functional Harmony Recognition of Symbolic Music Data with Multitask Recurrent Neural Networks, authored by Zhongping Chen and Li Su. And I'm Li Su from Academia Sinica, Taiwan. Okay, so in this paper, we consider the problem of chord function recognition. This problem can be regarded as an extension of the traditional chord name recognition. And why we are interested in this topic is because recognition of a chord function, it may provide more information that cannot be seen in just the chord name recognition. So for this example, here, this is a music expert, and we showed the chord function annotation below the step and the chord name recognition above the step. And from here, we can see that from the chord function recognition, we can observe there's a key change, and there's a dominant function, or there's even a preparation of a dominant chord function, and even there are some chord inversion, and this information cannot be observed from just the chord name. So to do this, we consider the chord function recognition problem as a multitext learning problem, as a chord function might contain many attributes. And to do this, we also compile and propose a data set containing all of the chord function annotations of the Beethoven's piano sonatas. And this data set is called BPSFH in short. Okay, so our annotation contains 5 attributes, including the keys, primary degrees, and secondary degrees like the 5 of 5, and also the chord quality, and also chord inversion. And we have to emphasize that, of course, such kind of annotation is not unique, but in our stage, we just use the chord function annotation by one music series. And so collecting the perspective from multiple annotations is still an ongoing work. Okay, so in the recognition test, we have multi-text learning, and here is some task sharing layer and task specific layer, all built in the bidirectional long short-term memory recurrent neural networks, and it outputs the likelihood of the 5 attributes. Okay, so in the experiment, we compare the performance of multi-text learning and like a single text learning. And here, the single text learning means that each attribute is learned by one separated neural network. So the result shows that using the multi-task learning, we can achieve a better performance for each attribute, and the performance of each attribute is higher than we just use a separate network to learn a single attribute. Okay, so for more detailed information about these works, please come to poster number 812. Thank you.
Thank you, Lee. The next talk, paper A13, will be given by Hendrik Schreiber from Tactron Industries, entitled A Single-Step Approach to Musical Tempo Estimation Using a Convolutional Neural Network.
Yeah, hello everyone. My name is Hendrik Schreiber. I'm going to talk about tempo estimation using a convolutional neural network. And traditionally, we have some sort of spectrogram and then do some sort of beat activation function or onset strength signal based on that, and then interpret that and get to some sort of tempo estimation. And what I'm proposing is kind of eliminating the middleman, meaning we just take a null spectrogram and then run that through a CNN, and that CNN does a classification into a tempo. So it's kind of one step, so to say. This is the architecture, and really what we're working on is an input that is only 12 seconds long. And then there is a short pattern matching phase. These are short convolutional filters. And there is a long pattern matching phase where we are using longer filters. And in the end, there is a simple dense classification, actually classification using a fully connected layer or multiple ones. Just to show that a little bit more detail, those modules there, multi-frequency or multi-filter modules, are based on an idea by Pons, Jordi Pons, maybe he's here. And it's basically a bunch of convolutional filters in parallel. The important thing for this to work is we are doing the convolution only along the time axis. So we have rectangular filters, and we're pooling along the frequency axis so that we summarize results from different frequency bands. So we've got to train this. We trained on a combination of 3 data sets. That is one LMD tempo, that's the first one. That is derived from Colin Raffel's LAC-MIDI data set. There are audio previews in there too. MTG tempo is basically another data set by Angelo Ferraldo. He used it's an EDM data set that was used for key. And then there is the extended ballroom set, which was released at the late breaking demo in, I think, New York. So during training, we do some tricks. We do a little bit of scale and crop data augmentation, meaning we are using the whole spectrogram for a song, compressing it by scaling it, have to adjust the label, and then just crop the 12 seconds. So here's an example. Because we're using 12 seconds, we can use overlapping windows and have local tempo estimation. And in theory, we're hearing something. But so that's the beginning, and it's very slow. And towards the end, like one can hear, it actually gets a lot faster. Here's another example, a little annotated, more complicated. This is dubstep. And there's a lot more going on, as you can see. And here again, we have 140 beats per minute, and then suddenly there is nothing. All right, so results are actually pretty good compared to the prior state of the art when you do accuracy 1, and they're not so good when you do accuracy 2 on a bunch of data sets. And I'd love to discuss that, why that's happening. So the summary. We consolidated the whole approach, having like multiple parts, just put it all in one CNN and make it a little easier. It's completely data-driven. We have fewer octave errors, which has been a problem in tempo estimation, and we can do both local and global estimation. Global estimation, by the way, just by averaging. Thank you very much.
Thank you, Hendrik. The next talk will be given by Magdalena Fuentes from Universidad País Sud and Telecom Tech. This is A14, and the title of the talk is Analysis of Common Design Choices in Deep Learning Systems for Downbeat Tracking.
Hello, everyone. My name is Magdalena Fuentes, and I'm going to talk about our work analysis of common design choices in deep learning systems for downbeat tracking. So, first, the general idea. What we propose is a systematic analysis of largely adopted variants in downbeat tracking systems. And for doing so, we took a fixed setup and changed one by one the different parts of it, avoiding the variation from using different training data or different training setups. So basically, we studied the temporal resolution of the input, or the future inputs, the architecture of the deep learning itself, the encoding of the labels used for training the networks, and the post-processing stage. So, going a little bit more in details, we propose a convolutional recurrent network, which we compare with a recurrent state-of-the-art network, block by block. We studied the temporal granularity of the input, in particular datum versus beat, which are both musical-inspired granularities. We studied the effect of using post-processing, in particular the well-known dynamic Bayesian network, and we did so comparing with the threshold and seeing its impact in the different configurations with the different architectures. And we propose an encoding, structure dense encoding, which has musical information on it, and we contrast it with one hot encoding that's typically downbeat or non-downbeat. So this is how the results look like. I'm not going into details right now with this, but I will be happy to discuss them in the poster, so approach it. And just as a heads up, we see that the temporal granularity has a very significant impact, and it relates with the architecture we are using. We see that the post-processing improvement depends indeed in the architecture and also in the data sets. In all cases, it improves a bit, but how much it improves depends on that configuration. We see that the structure encoding does not help particularly in the downbeat tracking, but it gives very promising results for multitask tracking, that it's beat and downbeat tracking. And thanks, and see you at the poster later.
Thank you, Magdalena. The next talk, A15, will be given by Andrew MacLeod for his second talk in this session. Andrew is from the University of Edinburgh, and his talk is entitled Meter Detection and Alignment of MIDI Performance.
Okay, thank you. Hello again. So I'll have two posters, but they're both next to each other out there. So feel free, I might be at one or the other, but just grab me and I'll be in the area at least. So what is the task precisely that we're trying to do here? Meter detection and alignment. So what I mean by that, we have an input, which is live performance, something like MIDI or piano roll, essentially anything that has notes, each of which have a pitch, an onset time, and an offset time. You don't have to have any other information. That's all we want. And the output is an alignment of those notes with a repeated metrical structure. So I have an example of what I'm talking about here on the left, or on the right, and that is the metrical structure of a 3/4 bar So this is a tree structure that has 3 levels, which is the bar level, the beat level, and the subbeat level. The reason I stop at 3 levels here is that this is enough to exactly define a time signature. We do implicitly, within the model another layer further down where each subbeat has 4 tatums, which is sort of the fastest pulse of a piece, but we don't model that explicitly. So the basic model is pretty simple. It's an HMM with 4 terms. The first 2 there are the transition function, and in general, they model the steadiness of a meter. So the first term models the probability of the tempo of a bar given the tempo of the previous bar. So we don't want huge changes there. The second term is the probability of the tatums. So we want, within each bar, we want the tatums to be relatively evenly spread out. We don't want big changes in tempo within a bar. The third and fourth terms there are the emission function, and they sort of model the likelihood of the notes given the meter. The first term being probability of notes given tatums, and that is just how well do the note onset times align with the tatums that we have modeled implicitly. And finally, probably the most important term, the probability of the rhythm. So we model that with an NLP, natural language processing inspired grammar from previous work. And essentially it looks at the context around each note to try and detect rhythmic stress and align that with metrical stress. So how do we do? So we use sort of an NF measure metric, and we compare against the previous state of the art is David Temperley's model. We have 2 data sets, one of metronomic MIDI and one of live performance MIDI, and we improve, our best model improves over Temperley's in both cases. And a quick example, so this is our best performing model. This is a prelude by Bach. This was live performance. And you can see we get the subbeats, we map them correctly in the correct locations, and the beats as well. We do get the bars incorrect. We guess a 2/4 time rather than 3/4, but we do pretty well in general. So in conclusion, musical rhythms and meters exhibit similar structure to natural language, and that's shown by the NLP grammar being able to model musical rhythms, and that the larger context provided by that grammar is important for the interpretation of musical rhythms. So again, what we're trying to do is find stress, and what the grammar does is it enables us to look at a larger context. So you can't say that a note is stressed in isolation. It's only really stressed in relation to what's around it, and that's what the grammar is able to do. Although the grammar does need a bit more data. We see as we add more data, the model improves. The code is available online, and again, please talk to me at either of my posters out there. Thank you.
Thank you, Andrew. The next talk, A16, will be given by Dasem Jong from KAIST in Korea. It's entitled Timbre-Based Approach to Estimate Key Velocities in Polyphonic Piano Recordings.
Hello, this is Dasem Jung from KAIST Korea. Our group is interested in transcribing performances of Western classical piano music from audio recordings. Among various features of performances, we have been focusing on 2 main features, the tempo and dynamics. The tempo and its variation can be transcribed by audio to score alignment. To transcribe dynamics, we have presented a score-informed NMF method in our previous work that estimates intensity of individual notes. By separating the spectrogram into weighted sum of the spectral templates of 88 keys, the system can estimate the intensity of each note. But there's a huge problem here. Unlike the temporal information in audio to score alignment task, the intensity of note is vulnerable to the recording condition. If someone changes the gain of the audio recording, that will also change the note intensity, even though the note is struck with the same velocities. But what you want to know is the velocities of a hammer stroke, which is more close to the performer's intention and also an important factor that decides the timbre of the note. To solve this problem, we propose a new solution that estimates the velocities of notes from piano recordings based on timbre feature, which is more robust to the change of the recording condition. The flow of our system is as follows. First, for given score data and audio recording, perform the NMF. As a result, we can reproduce a note-separated spectrogram for each note onset of the recording. Then, we can calculate note intensities and make intensity-normalized note spectrograms. The goal of upper part is to estimate the absolute dynamics of overall notes, which is independent to the recording condition. On the other hand, the goal of below part is to estimate the relative dynamics between the individual notes. Next, a simple FCN module takes these node-separated spectrograms. The FCN estimates MIDI velocity of each node. From the prediction of the FCN, the mean and the standard deviation are calculated. Combining the estimation of velocity distribution and the intensities, we can calculate the velocity of individual nodes. We tested our system on Xylan music data. The data set consists of 15 MIDI and audio recording pairs. The recordings were made in several years, thus make different recording conditions. We used the part of SMD as a training and validation set, and the remaining as a test set. The result shows that the velocity of estimation of FCM module was not accurate in note level, but the distribution of the estimated velocities was close to the ground truth value. By combining the statistic of FCM estimation and note intensities from NMF, the error got close to the upper boundary error. We also tested our system that was trained from SMD on MAPS Disclavia dataset. Since the MIDI velocity scale of two datasets is different, we cannot compare the prediction and ground truth straightforwardly. But as the figure shows, the statistic of prediction made a clear correlation with the ground truth. Our future plan is to develop a unified framework for automatically transcribing piano performances from the audio recordings. Thank you for the listening.
Thank you, Dassam. The next talk, A17, will be given by Francesco Bigoni from Aalborg University in Copenhagen, entitled Timbre Discrimination for Brief Instrument Sounds.
Good morning. Let's start with a bit of motivations. So listeners are able to identify musical genres within a fraction of a second. So what happens with the musical instrument timbre? And let's try out a simple task. I'll try to play a few sounds for you, and you'll have to mentally press a button that corresponds to the timbre you just heard. So let's try it out. So that should be a clarinet, an easy one. Now the second one. And the third one. And so the second and third snippet you heard were actual measured mean thresholds for above chance performance on these sounds. We used an adaptive method to estimate those and investigated the musical training effect on the task and related the degradation of timbre descriptors to perceptual strategies of the participants. We always include onset information in our snippets, and that's a debated choice. We can talk more about that at the poster. To estimate the thresholds, we use the simple up-down method. So if you look at the figure there, and think of this as a set of presentation for a single instrument sound, after each correct answer, you get a plus in the plot. The next presentation duration is decreased. And if you answer wrong, you get a minus, and the next presentation goes up in duration. Then we converge fast towards the threshold and oscillate there until a stock criterion is met. And then remember that in the actual experiment, the four timbres are interleaved. The presentations are all interleaved. We found an overall high performance from both groups, and this agrees with the previous literature. And we measured no effect of musical training. And our violin thresholds are significantly higher than guitar thresholds. So why don't we just use a classical model timbre perception for these very brief sounds, like multidimensional scaling? We could use the similarity ratings and fit them to a timbre space like the one in the figure. But essentially, we're looking at a different problem. So instead of finding the most prominent perceptual features, you are looking for the most informative ones. And if we think about a question here, instead of saying which instrument is playing this melody, we could say, I'd really like to play unison with guitar, and I hear a sound, and the question is, should I react to this and play or not? So how does our study differ from the previous studies in the field? We used an adaptive method because it is more time efficient, it's more accurate in estimating thresholds, and it seems to give consistent results. And the onset cognition significance in this context is debatable, and we can talk a bit more about it at the poster. And then I'll leave you with a question, which is, how do we extract meaningful features from these brief audio snippets? Thanks for your attention, and look for me at the poster if you have questions or remarks. Thank you very much.
Thank you, Francesco. And the final talk of this session, A18, will be given by Yunling Hung from Academia Sinica in Taiwan, entitled Frame-Level Instrument Recognition by Timbre and Pitch.
Hello, everyone. My name is Yunling, and I come from Academia Sinica, Taipei, Taiwan. And today I want to share with you my work, which is frame-level instrument recognition by timbre and pitch. And why we want to do the frame-level recognition? Because the previous instrument recognition method, if you give an audio and the algorithm will only tell you what kind of instrument is inside this audio. But for some of the cases, like music transcription, we want to know what kind of instrument is playing the note in each time frame. And the other cases is like music structure analysis. If we want to know the starting time and the ending time of each instrument in the audio. And that is all related to the instrument frame-level recognition. However, to our best knowledge, most of the instrument-related data sets don't have frame level. And that made this task more challenging. And the only data sets exist frame level is MelodDB, Missing Secret, and MusicNet data sets. But in our experiment, we choose the newly released data set, MusicNet, as our data set for two reasons. One is that it is larger than other two data sets, and the second reason is that it contains pitch labels. But why we need the pitch label? Because we want to further discuss how pitch information can help in the instrument recognition task. And that is basically our convolutional neural network structure. The input is a CQT, and then goes through some convolution layer. But here we preserve the temporal dimension since we want our output to be the frame annotations. And the max pooling is added after some convolution layer just for downsampling. And after go through some signal layer, our prediction is a two-dimensional instrument row. The X represents the time step, and the Y represents what kind of instrument is active in this time step. And like what we said previously, we can use the pitch information into our network. And we can extract the pitch information from the CQT and then use it as the additional information into our network. But how to use the pitch and how to extract the pitch information? Since the time limitation here, I'm not going to further discuss this. But I will just show you some brief example here. And look at the picture. The first row is the ground truth instrument row. And the second and third row is the prediction row. And the second row is only CQT as the input. But the third row is CQT and the pitch as the input. And we can learn from here that the pitch can help in two ways. First is that it can help to get the onset and offset information. Like we see in the red box here, if we add the pitch information, like the third row, and the onset and offset can be catched more precisely. And we can learn to, second thing is that pitch can help to catch the timbre information because pitch is related to the chromatic range and the harmonic distribution. And we can see in the blue box here, if we add the pitch information, then the confusion between two instruments can be eased. And if you have other further questions or want to discuss more, and please visit us at our poster section, which is A18, and thank you so much.
Thank you, Yunning. And can I ask you to give a round of applause for all 17 speakers for this morning session? They've done an amazing job of keeping to time, so we're exactly on schedule right now. And also thanks, of course, to the technical team who made sure everything ran smoothly. And over to Geoffroy for an announcement.
Short couple of announcements. Yeah, so first, thanks a lot to the speakers to keep on time. So actually, the average presentation time this morning was 3 minutes 30. So for the next speakers, be aware that you can use the full 4 minutes. You don't have to be stressed. We will not kill you, so no problem. So this morning, people were ahead of time. So actually, we are ahead of time. Use your 4 minutes. You can say many things in 4 minutes. Second thing, we're now moving to the coffee break. So the coffee break are served here and here. It is from now until 11, and then we will move to the poster session. Then we will, during the coffee break, reconfigure a bit this place towards posters. So I will ask the 3 first row here in front of me to go to the coffee break because we will have to change the configuration of the room. Have a nice coffee break. Thank you. And also, please, can you, there is a clock room there. So if you want to put your bag, don't hesitate. But don't let your bag here in the first row. Thank you.